So this is Jeff Hamrick at the University of San Francisco's Analytics program again. We're looking at the outputs from the fitting of the logistic regression model to the marriage happiness data. And I want to talk about the elements of this output. So let's start with the deviance residuals on top. So we do have residuals in some sense for a logistic regression model. They're simply not very useful though, since they don't emanate from some sort of principle of least squares minimization. So because we fit logistic regression models with maximum likelihood estimation, it's better to look at something that relates to maximum, the likelihood function, the log likelihood function in particular. So the deviance residual associated with some case is its value, the value of a particular case, which is a function of both its independent variable values and its dependent variable values, evaluated under the log likelihood function multiplied by -2. So deviance residuals should have properties similar to regular residuals, for example, symmetry. So when I look, for example, at this set of summary statistics for deviance residuals, I see that they're at least roughly symmetric, though perhaps not particularly symmetric. These are the MLE coefficients for the logistic regression model, including an intercept term. These are the standard errors associated with those coefficients, and these are the z-values that you obtain, basically by taking the ratio of the coefficient to the standard error. These are the p-values associated with those z-values, and as you can see in this case, we have three variables: church attendance, sex, and number of years of education, that connect in a statistically significant way to the dependent variable, which is whether or not you're happy in marriage. So I want to make a quick note about the way that R has handled these dichotomous variables that have been reported as strings. Namely, it has taken as a base case what comes first in the alphabet. So this value right here was rarely in church or often attends church. Because O comes before R in the alphabet, often attends church was taken as the base case, and this is indicating to us here what is the case associated with the number 1. In other words, to use sex as an example, the name of the variable was female. Male is the case when the variable female is equal to 1. When the variable female, which should really be called sex, is equal to 0, you have a female. So you can therefore interpret these coefficients in the following way. The negative signs on these two coefficients mean that if you rarely go to church and if you are male, you're more likely to report being unhappy in your marriage. How do I know that? Because the marriage variable was very happy and not as happy in marriage. Because N comes before V in the alphabet, V is the state equal to 1. That is, very happy in marriage is the state 1, and not as happy in marriage is the state 0. So these negatively signed coefficients are indicative that rare church attendance and being male are connected with more dissatisfaction in marriage. On the other hand, number of years of education positively connects to reported happiness in marriage. Let me talk really quickly about these quantities right here. This is the Akaike information criteria, which is determined in a way that is similar to the case for multiple linear regression models, except that the logarithm of sigma hat squared is replaced by the -2 times the value of the log likelihood function evaluated over all of the data. So AIC can be used to make apples-to-apples comparisons between different models fitted over the same data sets. Null deviance is related to the model that only has a constant coefficient, and residual deviance is related to our model, which has 3 independent variables. Okay? And what these two measures indicate to us is 2 different things. They indicate to us how plausible it is that we would see the data if the model were, for example, either constant or if it had the 3 independent variables that we added. And these are chi-squared statistics with this many degrees of freedom. So if we think about the null deviance model, what we see here is that the p-value associated with it is a little bit underneath 0.05, indicating that the data do not plausibly emanate from a logistic regression model with a constant term only. If we look, on the other hand, at the chi-squared statistic associated with the residual deviance figure that's been reported to us, we see that this p-value is large, meaning it is plausible that the data emanate from a logistic regression model that includes not only a constant term, but also these three particular independent variables. Okay? Now you might ask yourself, did we obtain statistically significant reductions in null deviance, in the deviance of the model by adding the three independent variables? This sort of indicates to us basically that we did. The fact that the p-value went from 0.04 to 0.75, but properly speaking, the way you would check this is to compute the difference in the chi-squared statistics for the null model and the model with the three independent variables. And you would compute also the difference in the degrees of freedom. So this p-value right here is exceedingly small, meaning you can reject the null hypothesis that the deviance of the model with only the constant term and the deviance of the model with the three independent variables added to it is the same. The deviances are not the same, and in fact the deviance of the model with the three independent variables is much lower, statistically significantly lower, in fact. So this is my brief review of the outputs associated with a logistic regression as operationalized in R. Let me know if you have any questions.